Students, now we are discussing in Telangana Genco 2024 question paper electronic devices and circuits questions. Question number 11 master question paper. The question is related to semiconductor theory. The question is related to semiconductors. So what is the question here means? Semiconductors question. What is the question means? Which one of the following statement is false? There are four options given. Conductors are formed using metallic bonding and has positive temperature coefficient. Yes, it is correct, but is asking which is false. Semiconductors are formed due to metallic bonding and it has low resistance. Third one, semiconductors are formed due to covalent bonding and it has negative temperature coefficient. Yes, this is also correct. Insulators are formed due to ionic bonding and it has negative temperature coefficient. So option 1, option 3, option 4 correct. But ఇక్కడ మనం ఏం అడిగాడంటే which following statement is false అన్నాడు. Semiconductors never formed using metallic bonding, they always formed with covalent bonding and it has low resistance. అది కూడా complete wrong కాబట్టి which is false అన్నాడు కాబట్టి here option 2 is false. Answer is option 2. Students, next question we are discussing. This is also semiconductor related question. Semiconductor theory question is asking here different types of currents. Drift current, diffusion current, pinch current, cutoff current. So what is the question means? Question number 12 master question paper. The motion of a charge carrier from a region of higher concentration to lower concentration leads to dash current anna. Students, here we are discussing in semiconductor theory two types of currents. One is diffusion current. One is diffusion current. Another is drift current. Here we are considering two currents. One is diffusion current, another is what? Drift current. Diffusion current will be considered due to non-uniformly doped, otherwise higher concentration to lower concentration. But drift current will be considered due to applied voltage. Here the question is higher concentration to lower concentration is mentioned, hence the current is diffusion current. Option 2 is the correct answer. Students, we are discussing next question. Question number 13 in master question paper. This is also related to semiconductor PN junction diode. Semiconductor diode question. Semiconductor diode question. See the question. The whole concentration in p-type gallium arsenide is given by P equal to 10 power 16 into 1 minus x by L per centimeter cube for 0 less than or equal to x less than or equal to L, where L is 10 micrometer. If whole diffusion coefficient is 10 centimeter square per second, then whole diffusion current density at x equal to 5 micrometer is. This is the question. Now what is asking here? Current density is asking. Diffusion current density. So here I am writing diffusion current density formula is Q into dP into dP by dx. This is the formula. Q into dP into dP by dx. What is Q? Charge of electron, that I am considering here 1.6 into 10 power minus 19, and diffusion constant is given as 10 centimeter square per second. Here all options are given in centimeter square, that's why I am no need to convert into meter. So I am writing as it is 10 centimeter square per second, and dP by dx, differentiation with respect to x. What is the p value? I am writing here 10 power 16 into 1 minus x by L. 1 minus x by L. So here I am writing this equals to 1.6 into 10 power minus 19 into 10, constant here 10 power 16, and differentiation of minus x by L with respect to L minus 1 by L. What is the L value is given? 10 micrometer. Micro means minus 6. All units are in centimeter. So I am writing 10 square. 10 into 10 power minus 6 into 10 square. This is a Q, this is a dP, and this is dP by dx. If you simplify all these, see 1.6 into 10 power 17, 10 power minus 19, that is 10 power minus 2. Here 10 square 10, 10 cube into 10 power minus 6, that is 10 power minus 3. That equals to I am writing 1.6 into 10 power minus 2 into 10 power 3, that is 10. So answer is 16 ampere per centimeter square. Option 2 is the correct answer, students. Next question we are discussing. This question is also related to PN junction diode breakdown mechanism question. PN junction diode question. We know that there are two types of breakdowns. See here, the question is related to breakdown. The avalanche breakdown occurs in lightly doped diodes where the depletion layer is dash and electric field is dash. We know that there are two types of breakdown mechanisms. One is avalanche breakdown mechanism, another is Zener breakdown mechanism. Here comparatively doping concentration, Zener diode is heavily doped than avalanche diode, we know that. Hence when Zener diode in reverse bias, width of the depletion region is inversely proportional to doping concentration. Hence when it is heavily doped semiconductor, width of the depletion region is small, decreases. But here avalanche breakdown diodes are lightly moderately doped semiconductor, hence the width of the depletion region is wide and electric field is low. So option 3 is the correct answer. Students, next question we are discussing here, question number 15 in master question paper. This question is related to optical devices, optical diodes. I am writing here. See, the question related to laser topic. Laser diode has a threshold level of current above which the laser action occurs and below which the laser diode behaves like a PN junction diode, highly doped Zener diode, light emitting diode emitting incoherent light, NCD emitting coherent light. So here these two devices, light emitting diode as well as laser diodes, both are optical devices, optical sources which are used to convert that electrical signals into light signals. So here he mentioned that when the threshold level of current greater, then laser action occurs. But here when the threshold level is current value is less than threshold level, then laser diode behaves like a answer light emitting diode emitting incoherent light. Light emitting diode emitting incoherent light. This is the option 3 correct answer. Next question we are discussing, question number 16 master level question paper. In N channel enhancement MOSFET at a fixed drain voltage, the drain current is. See here, if we consider N channel MOSFET characteristics, we know that the relation between depletion MOSFET as well as enhancement MOSFET. Here in depletion MOSFET there is a continuous channel between source and drain, but whereas in enhancement MOSFET there is no continuous channel between source and drain. The same thing here I am explaining by using graph. So here this is a transfer characteristics. Transfer characteristics gives relation between input voltage VGS as well as output current ID. Now the characteristics are in enhancement MOSFET like this. Up to particular voltage, that voltage known as threshold voltage. MOSFET does not conduct. Why MOSFET does not conduct? Because there is no conduction path between source and drain. Why there is no conduction path between source and drain? Because initially there is no channel exist between source and drain in enhancement MOSFET. This is the only basic principle, working principle difference in depletion MOSFET as well as enhancement MOSFET. Now read the question. In N-channel enhancement MOSFET, at a fixed drain voltage, the drain current is, see, the drain current is asking. So because at a fixed drain voltage, I am writing here VDS. So 0 at 0 gate voltage, and it increases with the positive applied gate voltage. This is the correct answer, because initially up to threshold voltage there is no drain current. Why there is no drain current? Because there is no channel between source and drain. After threshold voltage, when the gate voltage greater than threshold voltage, then drain current exponentially increases. Hence here option 3 is the correct answer. Next question. Question number 17. This question is also related to PN junction diode. PN junction diode. This question is related to PN junction diode. See here, this question, what is the question means? Yes, a germanium diode has a saturation current of 10 microamperes at 27 degrees Celsius. Then what is the saturation current at 127 degrees Celsius? Students, this question is related to PN junction diode question, question number 17, and the question is, a germanium diode has a saturation current of 10 microamperes at 27 degrees Celsius. Then find the saturation current at 127 degrees Celsius. Student, see here, why? Because I am explaining reverse saturation current. Reverse saturation current depends on temperature. As temperature increases, reverse saturation current also increases. If I01 is reverse saturation current at temperature T1 and I02 is reverse saturation current at temperature T2, then what is the relation between these two? Reverse saturation current and temperature means I02 equals to I01 into 2 power T2 minus T1 by 10. This is the formula. I02 equals to I01 into 2 power T2 minus T1 by 10. See here I am substituting reverse saturation current value is given as 10 microampere. I am writing 10 into 10 power minus 6 into 2 power 127, that is T2, minus 27, that is T1 by 10. So that equals to 10 into 10 power minus 6, 10 into 10 power minus 6 into 2 power 127 minus 27, 100 by 10, that is 2 power 10. 2 power 10, that is 1024 into 10 into 10 power minus 6, that I am writing 10 power minus 5. But all options are given in milliampere, because 10 micro it is not correct, 20 not correct, maybe answer in option 3 and option 4. So I am writing in milli. Milli means 10 power minus 3. So the remaining 2 digits I am writing like this, 10.24 milliamperes. So option 4 is the correct answer. 10.24 milliamperes is the answer. Next question, question number 18. The ratio of current of injected carriers into the base to the total emitter current is called, simple question, that is what? Emitter efficiency. This is a basic transistor fundamental question to explain a transistor operation. The ratio of current injected carriers into the base to the total emitter current is called emitter efficiency. So these are the questions related to electronic devices topics.